Hi everybody, welcome back. This is chapter 11, I think it's lesson 9, our final lesson in chapter 11. And we have to deal with section 8, which is suspensions and colloids. Basically what you have to know is that suspensions and colloids ain't solutions. They are not solutions. And I'll tell you why. You have to be able to distinguish why they're not solutions, okay? Here's why a suspension is not a solution. In a suspension, the particle is so large so that if you stirred it and let it sit, the particles are so large in a suspension, they would settle out to the bottom. Think of muddy water. If you went down to the creek and you got some muddy water in a cup and it'd look all solution-y, right? It'd be homogeneous at first, but the longer you let it sit, all the dirt would settle to the bottom. Well, not all of it, but a lot of it, okay? So solutions, the particles are so small that they don't settle upon standing. But in a suspension, the particles will settle upon standing. So in a suspension, the particles are too big that they settle out of the solvent if they're not constantly stirred. And a colloid is sort of in between. The particles are not as small as a solution, but they're smaller than a suspension. Oh. So in a colloid, the particles range in size between those of a suspension and those of a solution, okay? One of the ways we can distinguish is by this Tyndall effect. And if you have a colloid, the particles are big enough so that they scatter light. If you have a solution, the particles are too small and they don't scatter light. Okay, so you can shine a light through a solution and the light passes right through, but in a colloid, the light is scattered. That's the big difference, okay? The only other thing I wanted to do on tonight's video is that when I was looking and checking your notes, I noticed several of you did not have the boiling point elevation part filled in section 11.5. So I want to turn the camera onto the paper, and if you would just flip back to section 11.5, that way we can fill that in. I would also recommend you take a read through this section on colloids and suspensions, just so that you have a little bit more information and some examples of what is a colloid versus what is a suspension versus what is a solution. Just take a read through it. As always, of course, you should be reading. Okay, so let's pause for a minute, and then I'll get the camera set up, and we can fill in the notes. Action. All right, guys, sorry to have such a delay, but I had some computer issues. Although you don't know how long I was delayed, because it just picks right up where I left off. So anyway, this is section 11.5, and I noticed when I was going around, you guys didn't have these notes filled in, so I'll do my best to fill them in for you. It says normal boiling point is the temperature where the inside pressure equals the outside pressure of a substance. So it is the vapor pressure that is the inside pressure, right? Okay, pushing out. So if you have a container, like say you have a pot of water, isn't that beautiful, with the lid on it, on your stove, then there's gas molecules in here, right, pushing out on the walls of their container. So the force that these guys push out with is vapor pressure. And since we live in an oxygen environment, there's gas on the outside pushing in. And so the force that they push in with is known as atmospheric pressure, which typically is 1 atmosphere. So normally it's about 1 atmosphere here. If you live in Denver, then it's much less. But anyway, boiling will occur. A liquid will boil when its vapor pressure equals its atmospheric pressure. Then the liquid will boil. What non-volatile solutes do when you add them is they serve as anchors, right? So they prevent or reduce the evaporation, so they lower the vapor pressure at the same temperature, which ends up raising the boiling point, because now you have to get the inside hotter to make the two things equal. So non-volatile solutes raise the boiling point. That's why it's called boiling point elevation, not evolution. boiling point elevation, okay? And the magnitude of this elevation depends on the nature of the solute, so whether it's ionic or covalent, and the number of particles it dissociates into. The more particles, like any colligative property, the more particles, the greater the effect. And you should hopefully already have the equation written down, where delta T equals molality times Kb times I. You've been using it enough, I assume you have it down. On the next page you have freezing point depression, and they give you the equation, but many people said they didn't have the word filled in. But it is freezing point depression, so non-volatile solutes depress the freezing point. And another way to say depress, or another word for depress, is lower. They lower the freezing point. They prevent the molecules from coming together and forming those strong bonds that solids have. They run interference, they're blockers, so the molecules can't get together to make those strong bonds that solids have. All right, that's it for videos for chapter 11. You should be completing your test tonight. That practice test that I gave you, we did the first 9 questions. You should go ahead and complete those. And I will see you tomorrow. Have a great night, everybody. Bye-bye.